Good afternoon, everyone. Hope you had a good weekend. So ready to get started? Were there any questions over anything from chapter 2 so far? Over the homework or any other questions about any of the ideas or theories that we've been covering? Everybody's happy, huh? Can you all hear me? Yes. Okay. All right. So everyone's good. All right. Okay. So today, basic differentiation formulas, and then next time, product and quotient rules. So we're just chugging along here in chapter 2. And I wanted to also remind you, last class at the very end, I covered this thing, Pascal's triangle thing. I will be using this today, but we'll use it when we need it. All right. So for right now, don't worry about that. Let's get started. So chapter 2, section 3, basic differentiation formulas. So what I told you a while back is that, we started chapter 1 with the limit. We spent all this time doing the limit. And then when we got to chapter 2, I said, okay, there's a very special limit that we call the derivative, and it has to do with functions and finding slopes of tangent lines. So we spent all of 2.1 and 2.2 doing this thing called a derivative, but every time we did a derivative, we had to calculate a limit to do it. And if you did all the homework, you realize that can be, kind of a pain to do the limit every time, and the algebra can get messy. So from here on out, okay, from this point forward, we no longer need the limit to calculate a derivative. We're going to have shortcut formulas. So on your next exam, this is extremely important. On the next exam, if I ask you to find a derivative, and I say, find the derivative of this function using the limit definition, then that means you have to do what you did in 2.1 and 2.2. But if I just say, find the derivative of this function, and I don't tell you you have to use the limit definition, then you can use the shortcuts. So there's a distinction between the two. So good news is we get shortcuts now. Bad news is things get more complicated because we get harder functions. So we're starting out 2.3, basic differentiation formulas. This is me just telling you the same thing. We now have shortcuts. And so let's look at our very first one. And that is that the derivative of a constant is 0. So there's several ways for me to write this, all right? One thing I could do is I could say d dx, remember the notation that we were using, right? The Leibniz notation, use this d dx thing. If I say d dx and I put c inside parentheses, what this means is take the derivative of a constant c. So c is some fixed number. So maybe that's the derivative of 4, or the derivative of 10, or the derivative of -2, whatever. That just means take the derivative. Another notation I could use is just to put c in parentheses with a little prime mark on it. That would mean exactly the same thing. And so the question is, what is this, right? What is this? So I'm going to prove this to you. I'm going to prove the answer to this graphically. So if we were to think about what a constant function looks like. So if we were to take a function f of x equals some constant c, that should be a horizontal line, shouldn't it? It's always the same value. So whatever c is, let's say that's c, the graph of this function should be flat like this. And so if I go to any point on this graph, any value of x, and ask you what the slope of the tangent line is there, it should be parallel to the function itself. And since it's flat, that means that the slope of the tangent line should be what?
0.
0, okay? So the derivative of a constant is always 0, okay? So the derivative of a constant is always 0. So here's a specific example. If I said, what's the derivative of 4? You would say 0. If I said, what's the derivative of pi? you'd say 0, because pi is just a number, right? Pi is a constant. I say, what's the derivative of -2? The derivative of that is 0, all right? For any constant. That's the first shortcut rule. Ready for the next one? The next one is the derivative of the function x itself. In other words, what is the derivative of x? So I can do this one graphically as well. If I draw the graph of x, f of x equals x, this in college algebra is known as the identity function. And the identity function has this property that whatever you plug in is what you get out, right? So if you plug in 0, it spits out 0. If you plug in 1, it spits out 1. If you plug in 2, it spits out 2, right? And so on and so forth. So you get this perfect diagonal line. It's actually at 45 degrees there, is that angle right here. That's the identity function. And so again, if you go to any point on this function and you look at the slope of the tangent line, it should be parallel to that line. And what is the slope of this line? What's the rise over run?
1.
1, okay? So the derivative of x should be 1 always. Does that make sense visually? Okay, those are the first two shortcuts. The derivative of a constant is 0. The derivative of x is 1. Next rule is the big one. All right, so now we're going to move on. Those rules, these two rules, this rule and this rule don't really have names. This next rule does have a name. This rule is called the power rule. The power rule for differentiation. The reason I have to put power rule for differentiation is because when you get to Cal 2, there's a different power rule, and that's the power rule for integration or antiderivatives. That's a different class. Okay, so what is the power rule? Well, the power rule is this. We want to know what happens if you try and take the derivative of x raised to any power n. Another way I could write that, what is the power of x to the nth power, right? So that's what we need to figure out. Unfortunately, I can't show this to you visually because x to the n will look different depending on what n is, right? X squared would look a certain way, x cubed would look different, x to the 4th would look different. And actually, that n can be any power. It can even be a fractional power, like x to the 1/2 or x to the -2. So I can't show you a picture and visually kind of convince you of what's happening here. We have to do this algebraically, which makes it much more difficult. So I'm going to prove this rule to you, and then from here on out, you never need to know about the proof. It's just, I think it's worth us seeing what the answer to this is going to be. All right. So what I'm going to do is I'm going to say, okay, well, I want the derivative. I'm going to go back to the definition of the derivative. And remember, this is our function. F of x is x to the nth power. And now I'd like to know, what is f prime of x? What is its derivative? Well, the definition is limit h approaches 0, f of x plus h minus f of x all over h, right? That's our generic definition of the derivative. But for this particular function, x to the n, I want to start first plugging in x plus h, right? I want to plug x plus h in here, and then I have to do f of x in there, right? Or x into there. And so who wants to tell me what this limit should be here? Limit h goes to 0. What should the top left corner of my limit be? What should that right there be?
It would be x plus h n to the
X
nth.
plus h in parentheses, right? To the nth
Yes.
power. Good. And then I'm going to say minus what?
Just x to the n.
X to the n. That's f of x. And then all of this is divided by h. Does everyone understand that? If we're looking at the function x to the n, then if we plug x plus h into that function, we get x plus h to the n, and then we have minus f of x, which is just the original function x to the n. And we need to figure out what this is, right? We've got to figure out, like, what does this do? And right now, if we try and let h go to 0, we're going to get 0 over 0, which is bad. So how do we do this, right? Like, how do we do it? So when we look at this first piece, x plus h to the n, that means you're supposed to do x plus h times x plus h times x plus h times x plus h n times, right? But we don't know what n is, right? We don't know what n is. So let's look at last class, right? Remember I was doing this? And I said, hey, what's x plus h to the 0 power? 1. What's x plus h to the first power? Oh, x plus h. What's x plus h squared? And then I kept on going, right? And I was trying to get you to see a pattern here. Do y'all remember the pattern? Whatever the power is, right? Whatever this power is, that's what your x starts at, x to the 6th. And then as you move from left to right, the powers on x go down. And then the h's do the opposite. You don't have an h, then you have h, then h squared, then h cubed, then h to the 4th, 5th, 6th, right? So powers on x go down from left to right, powers on h go up from left to right. And then the other thing was to try and figure out what the numbers were, the coefficients, 1, 6, 15, 20, 15, 6, 1. And I showed you Pascal's triangle, right? And we were trying to find some patterns in this. So here's what I want you all to see. This is the only pattern I really need you to see to be able to show this to you. That if you look at all of these rows, notice what the second coefficient is in each of these rows. The second coefficient on the coefficient on the second term, 1, right? The second term here, 2, the second term here, 3, the second term here, 4, then 5, then 6. Do y'all see that the 1, 2, 3, 4, 5, 6 matches the power that we have here? Y'all see how that matches? Yes?
Yes.
That's the only pattern I need you to see. Now, let me write something else down now. What if we tried x plus h to the nth power? Let's talk about, first of all, what's the power on x? So on our first term, it'll be x to what power?
The n.
The n, right? Okay. And then we won't have any h's here, will we? No h's? And we will have a 1 in front, because remember, off Pascal's triangle, the first number is always 1. So that's what we have here. Plus, now, what is the number that's going to be in front?
N as well.
N, right? It'll be n in front. Then x to what power?
N minus 1.
Yeah, 1 less than it was, right? If it started out at n, it's going to be 1 less, right? It started at 6, the next one's 5. It started at 5, the next one's 4. So the power on the x will be 1 less than what it was. And do I have any h's? This time I have an h, right? Times h. Plus, are y'all following me on this? Y'all understand what I'm doing here? I'm going to move this down. Let's talk about the next piece. I don't care about the number, okay? Forget about the number in front. Don't even think about it. What's the power on x?
X minus 2.
N minus 2, right? So it's 2 less than what it started as. And then what's the power on the h?
H plus 1.
It'll be 1 more than
N
this one, right? So h just squared,
Oh, yeah.
right? And this keeps happening, right? I'll have some other number in front. I'll have x. Now it's n minus 3, right? It's 3 less than I started. And now the h has come up to h cubed. Are y'all following this pattern? X's are going down, h's are coming up.
Yes.
And then this will just keep going. So I'm going to put dot, dot, dot. right? Dot, dot, dot. This will keep going. Tell me what the very last one would be. What would the very last term of this be?
Would it be
So look-
h to the n or
H
1
to the
h
n,
to the n?
right? All h to the n, right? And there would be 1 in front of it. And then there's some stuff in front of it. I don't even care though, right? There's more stuff in front of this. In fact, you could write it this way. I'd have 1x left here, and this would be h to the n minus 1, and there would be some number in front of it. So in other words, my x's have been chipped down and got my x's have gone all the way down, and on the second to last term, I still have 1x. On the last term, I have no x's. And then the power in h here is n, but then the one before it is 1 less than n. Do y'all see that pattern? So agree with that? That's what x plus h to the n is. So I'm going to take this entire thing and I'm going to copy it and I'm going to bring it back over to this page that we were working on, because that is this, isn't it? That's what that is. So watch me write this. It's going to be equal to limit h approaches 0. By the way, this is not something that you would be expected to have just come up with on your own. Okay, I'm proving this formula to you. All you need to be able to do is use the formula once I show you what it is. So here we go. I'm going to put all of that here. My goodness. Okay, so all of this, I'm going to squeeze this a little bit further over here. Everything you see here, everything here is just the top left piece right there, right? That's all that is. Yeah. I still have on the back end minus x to the n. That's this piece, right? And then all of this over h. Okay. Now that may look like a disaster, but it's actually really nice. Watch. This x to the n up front cancels with the minus x to the n on the back. Those are gone, aren't they? Does anyone see what I can do now? Now that these are gone?
Common
Take
denominator.
out the factor of 8.
Yeah, every single one of these terms that are left, right? This one, this one, this one, all of the ones with dots, all of them, every one of them, all the way to the end. Do you agree that all of those have at least one h in them? Right? They all have at least one. The first one has just one h. The second one has h squared. The third one has h cubed, but the h's keep getting bigger. So I'm going to have at least one h in all of them. So I'm going to factor an h out. Okay. So I have equals limit h goes to 0. I factor an h out. When I pull an h out of this first term, I'm just left with n x to the n minus 1 plus some number. I don't know what that number is and I don't care. This is going to be x to the n minus 2. Now remember, I pulled this one of these h's, right? So I don't have h squared anymore. I have just times h. Plus then another number, I don't care what it is, x to the n minus 3. And this time I have h squared because I pulled one of those out, right? And I keep doing this all the way down until I get to the end. I'll have this x is here. I pulled an h out, so I'll have h to the n minus 2 because I took one away, one h out of here. And then the last one will be h to the n minus 1 because I took one of the h's away from this. Close my parentheses all over h. Now I can cancel the h. Last and very critical step. We're ready to let h go to 0, right? This term has an h in it. This term has an h in it. All of these terms have h's. Do you all agree that there's h's in every one of those? This has an h. This has an h. The only one that doesn't have an h is this one, right? So if I let h go to 0, gone, 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 everything here gone, gone, gone. And the only thing left is that part in green. which means that our answer is n x to the n minus 1. That is the derivative of x to the n. So the power rule says this. It says if you take the derivative of x to the n, or if you want to write it this way, x to the n with a little prime mark, your answer will be n times x to the n minus 1. So let's see this in action. As an example, if I wanted you to take the derivative of x cubed, here n is 3, right? So the way you do this is you use the formula. The formula says that the answer to this is the n, the power you started with, right, which is 3. And then the new power is 1 less than that. So a lot of times the way this is taught is that you just bring the power out as a 3, and then you subtract 1 from the power and it becomes x squared. And that's your answer, 3x squared. And we're done. And we're done. That's nice, isn't it? Let's do another one. What's the derivative of x to the 7th? Well, that's x to a power, right? So I'm going to bring the power out, 7, x to the 6th. Done. Pretty clean, pretty simple, yes? What about x to the negative 3? Derivative. Bring the negative 3 out. X to what power? Be careful. X to what power?
-4.
Negative 4. You have to subtract 1 from negative 3. So you're taking negative 3 and subtracting 1, you get negative 4. Now, I want to remind you, this is the same as writing negative 3 over x to the 4th power. Remember, if you have a negative exponent on your variable x, you can drop it down to the bottom, right? Let me do one more. What about 1 over x? What's the derivative here? All right, so that might look confusing, but really just think of it this way. Isn't 1 over x the same as x to the negative 1 power? And you want the derivative? Right, that's all that is. Take 1 over x, rewrite it as x to negative 1, and then use your power rule. So what would that be?
Negative x to the negative 2.
Yep, negative x to negative 2, which could also be written as negative 1 over x squared. Negative 1 over x squared. You like this? Isn't this better than using the limit? Let's play with this one for a second. This one, I graphed 1 over x. I'm sorry, I had 1 over x, right? That's 1 over x, and we said the derivative was negative 1 over x squared, right? There's the derivative. Let's see if this makes sense. Remember, we were talking last time about, graphing a function and its derivative together. If we were to, let's say we go to this function, the red one, and we go right here and we look at the slope of the tangent line, it'd be a negative number right there. Well, look, the derivative is negative. And if you move to the right, the slopes are still negative, but getting smaller and smaller. And that's exactly what's happening to the blue curve. They're negative values, but they're getting smaller and smaller and smaller. If you try and move to the left here, you notice that your derivatives are still negative, but getting very steep, which means it should be a very large negative value. And you can see that's what's happening here on this graph. The derivative is going very negative, very big. And the other side's, following the same sort of pattern. And I'm just trying to convince you it is working, okay? What we're doing is giving us the right answer. Okay, let me ask for another one. What about this one? 1 over the square root of x. What's the derivative? What about the square root of x itself? What's its derivative? What about the cube root of x? What's the derivative of that? What about the fourth root of x to the fifth, what's its derivative? Why don't you try those on your own? All of the problems I've given you here can all be rewritten. All of those can be rewritten as x to some power. And once you get it rewritten as x to a power, just use your power rule. I'm going to give you a few minutes to see if you can get these. Why don't you give me on the poll? Let me know when you've finished at least 2 of them. All right. So when you finish 2, just tell me yes. Here comes the poll. In case you're stuck, I'll remind you at the top here of a property from college algebra that if you ever have the nth root of x raised to the mth power, that this is the same as x raised to the m divided by n. This is a way you can always convert a radical into what's called rational exponent. So this is an algebra thing. You can use that on all these problems. I think I'm going to go like 1 more minute. Okay, got about half of you done. Look at the first one, 1 over the square root of x can be rewritten as 1 over x to the 1/2 power. That's what square root means, same as raising it to the half. Now I'm going to bring the x to the 1/2 up to the top to make it x to the negative 1/2. And then once I'm here, I can actually do the derivative because my power here, this is my n, right? The 1/2 here is my n. So I bring the negative 1/2 out front, and then I have to subtract 1 from negative 1/2. So this is a part you're just going to have to get good at this. Take negative 1/2, subtract 1 is the same as negative 1/2. Get a common denominator, subtract 2 over 2. And then now put the numerators together. 1 minus 2 is negative, or negative 1 minus 2 is negative 3. over the common denominator of 2. So this should be negative 1/2 x to the negative 3/2. And you can just leave it like that. You don't have to do anything else to that. So hopefully you got that. Are there any questions on that?
I kind of forgot how to put it in quadratic form. How would you put it? Like in the little, I don't know. How you
Back
call
in
it.
the radical form?
Yeah, radical. How would you put
Okay,
it?
so if I wanted to go back and put that into a radical, here's how I would do it. Negative 1/2 times, I'd rewrite this as 1 over x to the 3/2. I would drop the negative exponent down. And then I would use this property right here. That this is the same as negative 1/2 times 1 over. Now, the way I remember it is that whatever the denominator is, that's what goes on the outside. So it's the square root of x cubed. Now, you don't need to write square root. You don't need to put a 2 on a square root. It's implied. So this could turn out to be, we could write it this way, negative 1 over 2 square roots of x cubed. That would be correct as well. Does that make sense?
Yeah.
Okay. Good. I'm perfectly happy with this answer. Okay, on a test, I'm perfectly happy with that. But algebraically, everybody should be comfortable with that. You know, that these two, it's not that hard to get from here to here. Now let's look at the next one. The next one is the square root of x. So I can rewrite that as just x to the positive half, right? And then take its derivative. So the half comes out. X to the, you have to take a half and subtract 1. And when you do that, what do you get? What's 1/2 take away 1?
Negative 1/2.
Negative 1/2. Now on this one, I'm going to do the same thing we just did. Okay, I'm going to rewrite this as 1 over 2 times 1 over x to the positive half. But that just means 1 over 2 times 1 over the square root of x. That's what that means, right? And that just means 1 over 2 root x. So like I said, this answer in blue would be correct, but this answer in blue is also correct. Now, on this particular one that I just did, okay, on this one right here, this is a very important one because it comes up a ton, all right? We're constantly taking the derivative of square root of x, all right, in Cal 1 and Cal 2 and Cal 3. So here's what I'd like for you to do. I'd like for you to burn this into your brain, that if you take the square root of x and you take its derivative, the answer is 1 over 2 square root of x. Just go straight to this answer. This should be something you don't have to write down. You should just be able to spit it out like 1 + 1 = 2. That's how much it comes up, all right? So I'll say it again. The derivative of the square root of x is 1 over 2 root x. The derivative of the square root of x is 1 over 2 root x. 1 over 2 root x. 1 over 2 root x. All right? Burn it in. The next one isn't as frequent, okay? So what we would do here is we'd rewrite this as x to the 1/3 power, and then we would take the derivative. So 1/3 comes out, x to the 1/3 take away 1. And if you take 1 away from 1/3, you get negative 2/3. And I'm just going to leave it like that. If you did clean it up, here's what it would look like. It would be 1 over 3 times the cube root of x squared. Questions? It always makes me sad. I get like a little tear that comes out of my corner of my eye when I'm giving a test and somebody takes this derivative and gives me that answer. It always makes me sad because it makes me feel like that they weren't listening to me. That they just, for some reason, just did not want to listen to me and didn't burn it in. And then it comes back to haunt them later. When I'm doing things algebraically and I'm going straight to this and they just are adamant about doing that, it winds up hurting you later. So just memorize that. All right, last one up here. I'm just gonna go straight to the answer on this one. This one, let's see, it's to the 5/4, so it should be 5/4 x to the 1/4 should be your answer there. What do y'all think? Power rule. We can now take the derivative of x to any power. Good. Hey, does the power rule work for x? What did we say the derivative of x was? What did we say earlier? We said the derivative of x was 1, right? Right? That's what we said the answer is. Does the power rule work for this? What's the power on this right here? 1, right? Let's use the rule. 1 would come out. So I took the derivative, the 1 would come out. X to what power?
0.
0. And anything raised to the 0 power is 1. So this is 1 times 1, which just gives you 1, which it works, right? You know what's also cool? Remember how we said the derivative of a constant is 0, right? We said derivative of a constant is 0. One way you could convince yourself of that is to say, hey, look, 4 is the same as 4 times x to the 0. I know that that looks ridiculous, but 4 times x to the 0, what would the derivative of x to the 0 be? Well, what comes out? 0, right? And then it just kills everything off. And so you get 0. I'm just showing you that the power rule actually could have been used on the previous 2 that I showed you. Okay. So that is the almighty power.
I'm a little confused about that. So you said like anything raised to the 0 is 1, and then when you raise like the second one, it's 0. Like that one.
This
I
one?
just want to know the difference.
Could you try again?
What? I'm sorry. I heard like 2 different things there. I'm sorry. Bella? I didn't hear your question.
Oh, I'm sorry. So I'm a little confused. I may not see it, but you said like everything to the power of 0 is like 1.
Yes.
And why like x to the 0 in the 4th prime?
Yeah, so all I'm getting you to agree with, okay, let me write it this way. Do you agree that 4 is 4 times 1? Okay, now I could rewrite that 1 as x to the 0, couldn't I? I mean, like, it's kind of ridiculous for me to do that, but I could rewrite 1 as x to the 0, right? Now, if I asked you to take derivative of this, then you would use the power rule on this, right? X to the 0. So you would bring the 0 out front, and that 0 would kill everything off.
Yeah, because it's
right?
multiplying. Okay, gotcha.
Got it? And that's would match up with this answer that we would get, which is 0. Now, all you need to really remember is that derivative of a constant is 0. Okay, any constant is 0. The derivative of x is 1. And then derivative of x to a power is the power rule. And right, power comes out, subtract 1 from the power. Okay, the other one that comes up a lot, I already gave you. This one right here, this comes up a lot. Okay, so you know how I put stars next to this one? I said just memorize this one. I would say you should memorize this one as well. The derivative of 1 over x is equal to -1 over x squared. That comes up a lot more in Cal 2, but it will kind of creep its head up here a little bit. All right, good. We got the power rule down. Isn't that nice? We don't have to use limits for that anymore. Moving along, moving along. So we've got the power rule, here it is. And now we have what's called the constant multiple rule, all right? So let me show you what this is. I'm gonna write it down first and then I'll explain it. It says, say you're trying to take the derivative, and what you have here is some constant times some function. Not a constant by itself, okay? Not a constant by itself. A constant in front of a function. This rule says then what you can do is you can just put the constant out front and then take the derivative of whatever the function is. Okay, whatever that function is, you'll take the derivative of it. The way I like to look at this is by saying really what this rule is saying is that constants come for the ride. Okay, they come for the ride. You know what I mean by that? They're just gonna tag along the whole time out front. All right. I'll show you a specific example. As an example of this, if we wanted to take the derivative of 4x to the third, okay? Do you all see that we have a constant in front of some function? Right? It is a constant attached to some function through multiplication. According to this rule, what I can do is bring the 4 along for the ride. Okay, bring the 4 here. Okay, just bring it along. And then go ahead and take the derivative of the other part. The other part was x cubed. And I know the derivative of that is 3x squared. That's the power rule, right? So I do the power rule on that. There's my derivative. Right? The derivative of that is this, and the 4 just came for the ride. And then I can multiply the 4 and 3 together, and that'll give me 12x squared. You have to be careful because I already told you a minute ago that the derivative of 4 is what? What's the derivative of 4?
0.
0, okay? That's what happens when the constant's by itself. But when the constant is attached to a function with multiplication, the derivative of the 4 is no longer 0. It comes for the ride. All right, it's just going to come with us. And that happens for differentiation from here on out for the rest of your life. Constants just tag along. So let's do this one. What if we had what if I'm giving another example here? What if I wanted you to take the derivative of 8 square root of x? The 8 will come for the ride, right? So 8's going to be here. Times, now what is the derivative of the square root of x?
1, 2 square root of x.
1 over 2 square roots of x, right? And that 8, you can look at that 8 as being up in the numerator and the 2 as being on the denominator. So this reduces. This goes in once, that goes in 4 times. So you have a 4 on top of root x. This is the constant multiple rule. So what do we have? Derivative of a constant is 0. Derivative of x is 1. Power rule, constant multiple rule. That's where we are, right? Let's
Is
keep
the
going.
test going to say that specific rule and say, use this rule to find the answer?
No, the test is just going to give you a function and then you find the derivative. That's it. It won't say use any rule. You'll just have to know how to apply the rules. Okay, next rule, the sum and difference rule. Now, when you look at this, it looks freaking ridiculously bad, but let me just explain what it is on a different page. The sum and difference rule. And I'm going to do it in a slightly different notation. Let's say I have some function, okay, and I'm adding or subtracting some other function g, and I want to take the derivative. So I have 2 things being added or subtracted together. The sum and difference rule says this: you can take the derivative of the first function and then add or subtract, depending on whether it's addition or subtraction, the derivative of the second one. Now this rule, even though it looks simple, can be misused. Well, no, I shouldn't say that. This rule is simple. Let's not overcomplicate it. Let me give you an example. So let's say we have this. Let's say I want you to take derivative of x cubed plus x squared. Okay. This rule says, because you have addition right there, because you have addition, you are allowed to do them individually. You can do the derivative of x cubed and then derivative of x squared, and then you will just add those two answers together. So this means we should get what? What's the derivative of x cubed?
3x to the squared.
Yeah, 3x squared. And then I can say plus, and now the derivative of x squared,
2x.
2x, and we're done. That's the derivative. This is freaking awesome, okay? This is awesome. Now, I'm not really proving these rules to you. The only rule I proved, like this, where is it? This is an actual proof of the power rule. I have proven that this is what happens. All these other rules, you're just going to take them on faith, all right? If you'd like for me to prove them to you, come to my office hours. I'll prove every single one of them to you. They just take too long to prove, all right? We don't have time. I'd rather you practice with them. So what I'm going to do is I'm going to go to 2.2, the homework from last time. And I want to look at problem number 21 out of your homework. It gave you a function f of x was equal to x squared minus 2x cubed. And you were supposed to find the derivative of this function, right? You're supposed to define the derivative. So what you had to do was set up a limit, right? You had to do limit, h goes to 0, and then f of x plus h. I'm going to just show what it should have been. F of x plus h is x plus h plugged into the function. That's f of x plus h, minus f of x, which was x squared minus 2x cubed, all of that over h. And if you did this homework problem, you then had to expand x plus h, square it out, then you had to do x plus h cubed, multiply everything out, distribute things through, collect like terms, get things to cancel, and then you would have factored an h out, the h would have canceled, and I can promise you that your answer you got should have been 2x minus 6x squared. That's what you should have got at the end of all of that crap, and it probably took you a while to do that, right? But now we can do this without any of this. According to the rule, what we're trying to do is really take the derivative of these two things being subtracted, right? So the rule today is telling me, okay, I can take the derivative of x squared, then subtract from it the derivative of 2x cubed. The derivative of x squared is 2x, right? And then I have a minus sign. And then I need to take the derivative of 2x cubed. That 2 comes for the ride because it's attached to the x cubed. And then the derivative of x cubed is 3x squared. And if I just multiply the 2 and the 3 together, I get 6. And that gives you this answer. Isn't this better? Isn't this better? So I often have students, well, I'll have students ask me, have y'all ever heard of a class called business calculus? Business calculus? No? It's calculus for business. Okay, so there's a class called calculus for business. And students will be like, well, what's the difference between this and that class? Well, first of all, they spend a little bit of time with limits. They don't get deep into it, right? They do talk about limits, but when they get to derivatives in that class, they go pretty much straight to the rules, like to the shortcuts. They don't get tortured with limits for like 5 weeks like we have. All right. And that's the reason is because a business calculus student only needs to know how to find a derivative. They don't need to know the importance of the limit. And then the other difference is also that they don't deal with sine, like trig functions. They don't deal at all with sine, cosine, tangent. They stay just purely with polynomial functions and rational functions. Okay, so this is good, huh? We have this nice little Nice little rule now. So we have derivative of constant 0, derivative of x is 1, we have the power rule, we have the constant multiple rule, and we have the sum and difference formula. Let's keep going. No more rules yet. Let's do another example. Okay, what about this one? What if I gave you a function f of x equals, I don't know, what do you think? What if we had -3 square root of x plus 4 cube root of x minus 1/3 x to the 7th? And I asked you to find f prime of x. Well, that looks bad, but you actually have a plus here and a minus here, right? Which allows you to do each of them separately. Understand? You can do each one individually. Now, the sum and difference rule only had 2 things being added or subtracted, but does it make sense that if you have 3 things, you can do all 3 separately, and if you have 4, you can do all 4 separately? That makes sense to everyone? So it doesn't matter how many things you have. Remember, we call these terms in algebra. Terms are separated by addition and subtraction. That's a term. That's a term. So the idea here is that if your original function has a bunch of terms in it, you can do term by term differentiation. You can do differentiation of each term one at a time and just add or subtract those answers. So take a minute to see if you can get this. What is the derivative of this? So you're going to do -3 root x, you're going to take its derivative, plus the 4 cube root of x, take its derivative, and then minus the 1/3 x to the 7th, take its derivative, and see what you get. I'll give you a minute or two. Why don't you let me know when you have finished it? You don't need to clean up the answer. Just go ahead and take the derivative, see what you get. If you've got negative exponents, leave it that way. If you've got fractions, just leave them. Let me know when you've got the whole thing done. Wow, we've got 2 done already. Good, good. Okay, that's most of you. Any questions on this? Notice my notation. On the very first one, when I did the derivative, I brought the -3 for the ride, and then I just knew the derivative of the square root of x was 1/2 root x. On the second one, before I did the derivative, I rewrote the cube root of x as x to the third. So notice that I still have this in parentheses and the derivative prime mark on it to let you know I've not taken the derivative yet. And then on this one, I went ahead and just did the derivative. I brought the 1/3 for the ride and did the derivative of x to the 7th, which was 7x to the 6th. So the only one that I didn't take the derivative of on the second line is this one. And then on the third line, I actually did the derivative. I brought the 1/3 out, subtracted 1. And then here I just cleaned up some fractions. So no questions? No? So I'll show you something kind of cool in Desmos, right? I've been using this software to graph functions. Here's the graph of that function, okay? And we just found the derivative of it, right? This is pretty cool. In Desmos, look what I did. I wrote f of x equals, and then I put the function here. In Desmos, if you put f prime of x, it'll graph it. Like it'll actually graph the derivative for you. It doesn't tell you what the derivative is, but it actually graphs it for you, which is kind of nice. Okay. No questions? No questions? All right, I have a trick question for you then. How about this one? F of x equals 3x squared minus 4 root x plus 5 all over x. Find f prime of x. I want you to think about it, okay? Just think about it for about 30 seconds. So I'm going to write something down. I'm going to write it in red, okay? In big red, because this is wrong, all right? But I want you to look at what I write and then tell me if you understand what I'm doing here. What did I do?
You took the derivative of every single one of the numbers.
Yeah. I just took the derivative of everything, right? So I took derivative of that, and that, right? That seems reasonable, right? That seems reasonable, but it's wrong. And here's why it's wrong. I have only given you a rule, right? The only rule that I've given you allows you to take the derivative individually, piece by piece, if you have addition and subtraction only, right? I have not talked to you about how to handle division, have I? I have not. In fact, I'm going to talk about that next class. I'm not even going to talk about it today. You are not allowed to do this. If you have division, you are not free to just take the derivative of the top and bottom separately. I'll say it again. If you have division, you are not allowed to take the derivative of the top and bottom separately. If you have division, you are not allowed to take derivative of top and bottom separately. All right, it's 3 times I've said that. So what do? Well, in this problem, there is a way to do it, okay? There is a way I can do this problem, but it's not this, okay? It's not that. Here's what I would do. Because of the way the problem is presented to me, there is a way that I can rewrite this problem like this. 3x squared over x minus 4 root x over x plus 5 over x. Now I'm only allowed to do that because I have a single term in the denominator. if we had multiple terms in the denominator, you cannot do that. I guess what I'm saying is this. If you were to write this way, this cannot be split up into 3 fractions. This does not become x over 3x squared. Shit, I don't even know what you'd write next. X over 4 root x, and then plus like x over 5. This is completely wrong. You are only allowed to split fractions up, or split a fraction up, if you have a single term in the denominator. Do you all agree with that? Do y'all understand why you're allowed to do that? Yes? Okay. Now, once we're here, I'm still doing algebra right now. I'm not doing any calculus yet. I can simplify this. Because I have an x squared over x, I can cancel one of the x's. That just turns into 3x. And then I have root x over x. Okay, what is root x over x? Root x over x is the same as x to the half over x. And I can write that x is x to the 1. And then there's a property from algebra that says if you have x to a power divided by x to a power, you subtract the powers. So that's really x to the negative 1/2, right? The square root of x divided by x is the same as x to the negative 1/2. So I can rewrite this as minus 4 x to the negative 1/2. And then the last one I can write as 5 x to the negative 1, because I can put that x and push it to the numerator as x to the negative 1 power. Any questions on that? Do you all understand how that's just algebra there? I'm just massaging the original function into something that now looks like something plus something plus something, or something minus something plus something. It's addition and subtraction. I no longer have that big division that I had before. So now you can follow the rules. Now you can do the derivative, and I'll give you the green for this now. So the derivative of this will be, what's the derivative of 3x?
Just
Just
3.
Just 3. Yep, just 3. So you could say the 3 comes for the ride, and then derivative of x is 1. So 3 times 1 is 3, right? What about the next one? Negative 4 comes for the ride. You really start to get to a point where all you're doing is taking this power and popping it out front and multiplying these two together. So if we multiply this and this together, negative 4 times negative 1/2 is plus 2. X to what power? I'm actually taking the derivative right now.
It would be 3 over, well, negative 3 over 2.
Negative 3 over 2. And then same thing here, bring this power out front, hit the positive 5 with it, becomes minus 5, and then x to the negative 2. I subtract 1 from x, or from, sorry, subtract 1 from negative 1. There's my derivative. Okay, I need to move on. We know the derivative constant is 0, derivative of x is 1. We know the power rule. We know the constant multiple rule. We know the sum difference rule, right? We know that if we have division, we can't do anything yet. Next class. So there are a few more things we need to know how to take the derivative of here in this section. So I'd like for us to talk about this. What if the function we have is the function f of x equals sine x? What is the derivative of this? Well, we haven't talked about that, right? I haven't given you anything that deals with trig functions. I've only told you derivative constant 0, derivative of x is 1, power rule, constant multiple rule, sum and difference rule. That's all I've given you, right? There's nothing yet that deals with this. So we need to figure out what it is, right? Well, I can't show you a picture. So I'm going to prove this to you kind of like when I did this. For sine, I'm going to prove it to you, okay? So for this one, I'm going to prove it. And then for the rest of the trig functions, you're just going to have to believe me because I don't have time to prove all of them, all right? I will prove sine though. So I'm now going to try and figure out what is the derivative of this. So here we go. The derivative of this sine function, f prime of x, should be the limit as h goes to 0 of f of x plus h minus f of x all over h. That's our generic definition. Okay, that's the limit as h goes to 0. Okay, f of x plus h. We plug x plus h into the sine function, which gives me sine of x plus h, right? That's what happens when I replace x with x plus h and push it into the sine function. I subtract from that sine x. That's the original function. And I divide this by h. If we let h go to 0 right now, we will get 0 over 0. It'll be bad. Unfortunately, there's no algebra you can do here. Please don't do this, okay? This is not sine x plus sine h, okay? That is not right. You do not distribute sin through here. I think we talked about this before, that this is not allowed. Okay, so I can't do that. And so I need to do something else. So here's what I'm gonna do. Check this out. It's pretty cool. You took pre-cal, right? You passed pre-cal. That means you're here, right? So in pre-cal, there was a formula in pre-cal right here. It's reference page 2 on our formula sheets. Maybe this formula looks familiar to you. This is called in pre-cal, I think they call it the sum and difference formula, but here they call it the addition subtraction formula. Sum, add, difference, subtract. So that formula right there allows me to write sine of x plus y as something new. And I'm going to use that right now. Again, I wouldn't expect that you would know how to do this, like that you would do this on your own. You're just watching me do it, okay? So I'm going to use that formula right there. Just remember that for us, we have sine of x plus h. So all the y's here get replaced with h's, right? That's basically what I'm going to do. So this becomes sine x cosine h plus cosine x sine h. That's what this is. And then I still had minus sine x all over h. You with me? Okay, now what? Hold on. I forgot what to do now. Okay, so I haven't proven this since I don't know when it was. Last time I taught this, maybe. I don't know. I don't always prove the sine one. Okay, so here's what I'm gonna do. Let me just think about this. Yeah. Okay, so here's what I'm gonna do is do sine x cosine h minus sine x all of this over h plus cosine x sine h all of this over h. Okay, so all I've done here is I've put this piece and this piece together. I've moved those together here and here and put those two over h. And then I put this blue one over here and put that over h. So I've like split this fraction into two fractions. Do y'all agree I can do that algebraically? This is okay? Any complaints or gripes about that? Next thing I'm going to do is I'm going to recognize that h is going to 0, right? H is the thing that's changing. X is not in here, right? H goes to 0, but x is just stuck, whatever x is, which means the h has no impact on the h has no impact on anything that has x in it. So I'm going to write this like this now. Limit h goes to 0. Watch. I'm going to factor sine x out of the top. Right? These both have a sine x in them. And then over here, there's nothing to factor out. I'm just going to rewrite this kind of in a different way. Cosine x times sine h over h is the same as writing cosine x times sine h over h like this. So those are the same thing, right? Now h is going to 0, right? Maybe I should have this all in parentheses here. H is about to go to 0. I want you to focus your attention on this over this and this over this. Let's start with the second one, this one right here. If h goes to 0, what does sine of h over h go to? Drum roll. Ash, good. It goes to 1. Remember, that was sine junk over junk. Remember that thing we learned? That's sine junk over junk. So we know that this piece right here goes to 1, and in front of it is cosine x, right? This was one of those very important limits I told you you need to know, right? Now, does anyone remember this one? What cosine of h minus 1 over h goes to?
0.
0, Ash, 0. Very good. That goes to 0. And if that goes to 0, we get sine of x times 0, which kills that off. And then we have plus cosine of x times 1. So what's your answer?
Cosine of x.
Cosine of x. Cosine of x. What? The derivative of sine of x is cosine of x? What? The derivative of sine of x is cosine of x? That doesn't seem like that could possibly be right. Let's see. Sine x, right? There's sine x. Here's cosine x. Let's go back to last class. If I gave you sine x and I asked you to graph its derivative, right? Graph its derivative. Here's what you would do. You would go to all the places you know about. Do you all agree that on this is the sine function we're looking at here. Do you agree that at all these peaks and valleys, the slope of the tangent lines there would be 0, right? Which means that the derivative there would be 0. So I should have a 0 here, a 0 here, a 0 here, and a 0 here. Agreed? Okay, let me go to another point. How about at the origin right there? What does the slope of that tangent line look like? That slope, it's positive, right? And doesn't it look, yeah, red, doesn't it look like 1, like a perfect diagonal slope there? Well, it is. It actually turns out it is. It's 1. And then as I move from here to here, the slopes of those tangent lines are, oops, the slopes of those tangent lines are still positive. God, that's not drawing right. But look, they're shallowing out, right? They're positive slopes, but they're getting smaller. So it's positive numbers getting smaller and smaller, headed towards 0. And then once I get to here and get to the other side, now my slopes are negative, aren't they? Negative, negative. And when I get to about right here, it's like a perfect diagonal. So I should get like -1, something like that. And so they were small negative numbers going towards -1. And then as I keep moving, these get shallowed out again. So they're negative slopes headed back to 0. And then I could continue doing this for the whole graph. And if I put them all together, I get the cosine function. It's pretty cool, if you ask me, right? That when you look at the sine function and you look at its derivative, the derivative is actually the cosine function. Okay, so we need to know that. Everyone needs to know that. Burn it in. Derivative of sine of x is cosine of x. What do you think about the derivative of cosine of x? So what if I started with this and I said, go find me the derivative of this? If we followed that same like method, we know here, 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 and here we have slopes that are 0, right? So we should have x-intercepts on our derivative. Understand? So far, does our sine function do that? So far, does it look like that's cosine? Does it look like the sine function has those x-intercepts? Yes, right? So let's see, maybe the derivative of cosine is sine. Well, what happens here? If I start moving to the right, I'm looking right here. If I start moving to the right, I get negative slope, don't I? Negative, 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 and it looks about there to be -1. So it was negative values to -1, and then it starts shallowing out again back to 0. And then once you get on this side, now you have positive slopes, and then you get to here, it's about 1, so it goes like that. And then once we get here, it's still positive, but they're shallowing out, so it goes back here. Is that sine?
No.
No, it's not sine, but what is it? It does kind of look like sine. Doesn't it look like sine flipped over? It looks like sine reflected over the x-axis, doesn't it? So the derivative of cosine looks like sine, but reflected over the x-axis. When we want to reflect things over the x-axis in algebra, we put a negative in front. And so without me proving it to you, the derivative of cosine of x is negative sine of x. I didn't prove it. I could prove it with the limit, but it'll take too much time. Okay? Derivative of sine of x is cosine of x. Derivative of cosine of x is negative sine of x. Burn them in, okay? How many other trig functions are there in pre-cal? There's sine, cosine, tangent, cosecant, secant, cotangent, right? There's 6 trig functions in pre-cal, and each one of them has a derivative. I've covered 2 of them. Derivative of sine of x is cosine of x. Derivative of cosine of x is negative sine of x. You ready for the derivative of tangent? I'm not going to prove it to you. I'm just going to give it to you. All right. Derivative of tangent of x, secant squared x. Here are the other 3. The derivative of cosecant of x is negative cosecant of x cotangent of x. The derivative of secant x is secant x tangent x. The derivative of cotangent x is negative cosecant squared x. For sure, you should have these memorized. Here, let me bring these up. I'm going to get them all together here. These are all on your formula sheets, by the way. Okay. Yeah, I think I should show you the formula sheet real quick. On your formula sheet, on reference page 5, all the rules that I've given you today are here. Derivative of a constant is 0. If you have a plus between 2 functions, you can break it up into 2. If you have a minus between 2 functions, you can break it up into 2. If you have a constant, it comes for the ride, right? Power rule. We've covered all of those today, all right? We have not covered, okay, so we still have not done this or this or this. That's these 2, product and quotient, are next class, and chain rule is the class after that. So we know those derivatives in yellow as of today. And if you continue to scroll down, you can see here the derivative of sine is cosine, derivative of cosine is negative sine, derivative of tangent secant squared, and then the other 3 are here as well. And then there's a whole bunch more, but you don't need to know any of these yet. You get to Cal 2. In Cal 2, the first week, we cover all these. We just say, okay, let's just knock these all out. These are all new derivatives that you learn in Cal 2. All right, so the things we still are going to learn in this class are the things in red, okay? Everything in red here, we will learn in this class. Everything below here in black is reserved for Cal 2. First week of Cal 2. Maybe even, well, yeah, usually about the first week. Okay? Questions? So what I was saying was that you should memorize these 3 for sure. Have these memorized. So by next class, if I ask you what's the derivative of cosine, you shouldn't have to go look something up. It should be negative, derivative of cosine is negative sine. If I ask you what's derivative of sine, you say derivative of sine is cosine, right? Derivative of tangent, secant squared. Those 3 for sure, you should have them right at the tip of your tongue. The other 3, they take a little bit of time to memorize, but you can do that. Questions? Right. If f of x equals, let me see here. Yeah, if f of x equals x squared minus the square root of x, find the equation of the tangent line at, let's go with 4:14. All right, so we're going back now to earlier in this chapter where I said, hey, go find the equation of the tangent line. So in order to find the equation of the tangent line, you're going to need to use this formula, y minus y1 equals m times x minus x1, right? That's the generic formula we use to find the equation of any line. We need to know what x1 and y1 are, so we need a point, but that's already given to us. That's x1, this is y1. So we have the point taken care of. What's the only other thing we need?
The slope.
The slope, right? We need to find the slope, right? So we need to find this slope, which for us is really the derivative of this function at x equals 4, right? To find the slope of the tangent line at this point, we need to figure out what the derivative is and plug 4 into that derivative, and that'll give us our exact slope. So let's go get the derivative, right? The derivative of this should now be easy, shouldn't it? Now that we have the rules, we have subtraction between these two, we can take derivative of each one. So this should be 2x minus 1 over 2 root x. And now to figure out the slope of the tangent line at 4, I plug 4 into this and I get 8. Let me do it this way. 2 times 4 minus 1 over 2 times the square root of 4, which is 8 minus 1 over 2 times 2, which is 8 minus 1/4, which is 31/4, I believe. You have to get a common denominator between these two. That's your slope, right? So I'm ready for the equation. Y minus 14 equals 31/4 times x minus 4. That is the equation of the tangent line at that particular point. Do you see how fast it works now that we have the shortcut? Like we can just get that derivative really quick. Questions? All right, I want to just, let's just go verify it. Let's go look at that function. It was x squared minus the square root of x. And we were looking at the point 4:14, which should be here. Right there. Okay, there's that point. And we got the equation y minus 14 equals 31/4 times x minus 4. There it is. Looks like we did it right, yeah? Does that look like the equation of the tangent line right there? Goes right through that point, looks tangent to the curve. Another question. If f of x equals x squared minus the square root of x. Find f double prime of x. So what am I asking you to do here?
Find the second derivative.
Yeah, take the derivative of the derivative, right? Now that's the same problem we had just a minute ago, right? So we already know from previous example that the derivative of this was 2x minus 1 over 2 root x, right? That's our derivative. We have to take the derivative again, don't we? Now, when you take the derivative again, notice on this second one here, if I'm going to take the derivative of that, I'm going to need to rewrite it as 1/2 x to the negative 1/2. In other words, I've got to bring that root x back up to the top. That way I can use the power rule on the derivative. Who wants to tell me what the second derivative then would be? So what's derivative of 2x?
1.
2 times
Right.
1.
Oh, 2
Right.
times 1, yes, 2.
So just 2, right? And then on this one, we rewrote it and now run your power rule on that. So who wants to give me that one? I'll put a minus sign here, I guess. I'll put a minus sign here. And then I'm just bringing that down. What is just the derivative of this? I'm not calling on anyone today. I'm just letting y'all respond, but I think next class I'll probably be calling on people. So
Is it -1 over x3 over 2? X. to the
where'd you get the
power-
-1 from? So you have this 1/2 comes for the ride, right?
Yeah.
And then this power comes out. So -1/2 comes out, right?
Yeah.
And then x, now you subtract 1 from that power and you got -3/2.
So do I put it at the bottom or no?
Yes.
I just
Let's put these two together though. Those two would
Okay.
become -1/4, right?
yes.
And then you have x to the -3/2. Y'all could leave it just like that. Or you could write it as -1 over 4 and then square root of x cubed. That's the same thing. But this goes here, doesn't it? So you're going to have a double negative here, -1/4 x to the -3/2. So when you put those minuses together, you get plus 1/4 x to the -3/2. That should be your second derivative. Questions there? One more thing I want to show you. Okay, you ready? This is going to be kind of like, whoa, what the hell? That should get you, that you should be able to do most of the homework with that. I think you'll be okay with the homework with everything we talked about. Just remember that yeah, okay. You might run into some little road bumps, but nothing major. All right. So I want you to consider this problem here. What would happen if we took the 45th derivative with respect to x? The way you write this is really confusing. What if I wanted you to take the 45th derivative of sine? Yeah, the 45th derivative of sine. And you know what? Someone's going to sit there and try and do 45 derivatives. So let me change it. Let's go the 451st derivative of sine. That way I can stop someone from trying to do it by hand, okay? I have 9 minutes. Let's see how far we can get with this. Computer science majors, right? Pay attention, right? Because there's something I'm going to do in here that's important. Let's start taking some derivatives to figure out what the hell's going on here. All right. Let's say, what is the first derivative of this? Well, you know what? Yeah, let's write it this way. Let's say y is sine of x. Okay, that's the original function. What would the first derivative of that be? So what's the derivative of sine? We just went over
Cosine
this.
x.
Cosine of x. Okay, great. Now, what's the second derivative? Well, what's the derivative of cosine?
Negative sine x.
Negative sine x. Why are you doing that? This thing irritates me. Negative sine x. There we go. Okay. And then what's the derivative of that? So what's the third derivative going to be? Think about that
Negative cosine x.
It'll be negative cosine of x. Exactly. That negative in front is like a -1. So when you take the derivative of this, the -1 comes for the ride. And then the derivative of sine, we already said was cosine. That's that constant multiple rule, that the negative comes for the ride. So now we have negative cosine x. Fourth derivative. Watch my notation here. I'm not going to do 4 prime marks. I'm going to start putting these things, the number in parentheses. Do I remember when I told you about that? About the notation? Fourth derivative. Okay, so again, constant multiple. The -1 comes for the ride. So just ignore the -1 for right now. What's the derivative of cosine of x?
Negative sine x.
Negative sine, right? But we have a negative, right? So it's like negative sine of x, which turns out to be
Sine
just
x.
sine x, right? And now we're back to where we started, right? So now it should just repeat the pattern. The fifth derivative should be cosine x. The sixth derivative should be, well, what came next? We had sine x, then cosine x, then it should be negative sine x again. And then the seventh derivative would be what, negative cosine of x. And then the eighth derivative would be, well, we'd be back to sine, right? You all following me here? Okay. So let's see what's in common. When are we getting sine? We get sine here, here, and here, right? So would you all agree with this? We get sine x as an answer if the derivative that we're taking is, well, if we don't take a derivative at all, okay? This is the original function. We call this the zeroth derivative. The first derivative is you just take the derivative. The zeroth derivative means you don't take the derivative at all. So we will get an answer of sine of x if the derivative is 0 for what's next? What do you think the next one would be?
8 and 12.
I'm sorry, I forgot to put the 8. 8, then what?
12.
12, right? Then what? 16, right? They keep going up by 4, right? So if we do any of these derivatives, right, we are going to get sine. Do y'all understand? You sure? You sure? Okay, now what about cosine? We'll get cosine if the derivative we're taking is, let's see, when does cosine happen? First derivative, cosine, fifth derivative, and it would have appeared next here, wouldn't it? Have been the next one here? So that would have been the ninth derivative. So we would get this if we take the first derivative, the fifth derivative, the ninth derivative. What would be the one after that?
13th.
13. Those are going up by 4, right? Each time. Okay, and then what's the next thing that happens? Negative sine. That happens there, So we get negative sine of x if the derivative we're taking is the second derivative or the sixth derivative. What would be the next one?
10.
10th, right? And those are going up by 4, right? 14. You got it? Understand? We have one more. We could get negative cosine x, and that's happening when the derivative is 3, 7, 11, 15, ... That's when we get negative cosine of x. Do I need to clarify anything that I've done here? We're not done. We haven't answered the question, right? But what I've established is patterns, right? I know what happens with certain numbers for derivatives. So what I really need to figure out now is this number 451, does it live in this list, in this list, in this list, or in that list? Which list does it live in? Is 451 in the first one, second one, third one, or fourth one, right? Can somebody tell me what list it's not in, just to start?
The first one,
Can't be in the first, why?
because they're all even.
Okay, and then what about the third list?
That one too.
That one's
They're
even.
even as well, right? So it can't be in those two, right? So it's either gotta be in this one or this one. So the answer is either cosine or negative cosine, right? Yes, I agree with that. Yeah, I agree, but there's a better way to do it, okay? There's a better way to do it. And this is why I said computer science people pay attention. I'm gonna do something called modular arithmetic. Now, notice that for all of these lists, the important jump between number and number here was 4, right? All of these lists jump by 4, 4, 4, 4, 4. So what I'm going to do is something, like I said, called modular arithmetic. And here's the way it works. If I write this down, so you may have never seen this before, most of you probably have not. If I write n mod, let me do it a different way, n mod p. Let me do that. So n mod p. Then what this is the remainder left if you divide n by p. Okay, so this is new notation for a lot of you. Okay, n mod p. Let me show you how it works. If I write 12 mod 3, then what I do is I do 12 divided by 3. What's 12 divided by 3? 4,
4.
right? Is there any left over?
No,
No. Okay, so that would be 0. There's no remainder. But if I do 11 mod 3, how many times does 3 go into 11?
3,
3 times, but you would have how much left over?
2,
2. Okay, what would 10 mod 3 be?
still, well, it would be 1.
It would be 1 because 3 goes into 10, what, 3 times with 1 left over? So it's the remainder that's left over. Does that make sense? When you do modular arithmetic like this, whatever this number is dictates how many answers you're going to get out. If you do mod 3, the only answers you can get out are 0, 1, and 2. That's it. You can only have a remainder of 0, a 1, or 2 for any number. Give me a number. Let's do 127 mod 3. Okay, I promise you the answer is either 0, 2, or 0, 1, or 2. So how many times does 3 go into that? I do 127 divided by 3, it goes in there 4. 12, then bring down 7, it goes in there 2. That's 6. I have a remainder of 1. So this would be 1. Okay. I'm out of time. I want you all to look at these numbers. Okay. If you look at this list right here, remember I said the jump was 4? In all these lists, the jump is 4. I want you to consider taking every single one of those numbers in that list and modding them for mod 4, mod 4, mod 4, mod 4. What are you going to get as an answer for all of them?
0.
0. You get 0 for all of those. And guess what happens if you mod all these for? The 1, 5, 9, 13. Guess what you get if you mod all those?
1.
1. And what about these? If you mod these 4, you're going to get 2. And if you mod all these 4, you're going to get 3. Understand? So all I need to figure out is what is 451 mod 4? So how many times is 4 going to 451? So it goes in there once, right? I get 400, then 51. That goes in there once. I get 40. I get 111. That goes in there twice. That's an 8. And I get a 3 as a remainder. So 451 mod 4 was 3. So which list does it live in? First, second, third, or fourth?
The fourth.
Fourth. It lives with all the mod 4 ones. I mean, sorry, it lives with all the ones that when you mod 4, you get 3, which means the answer is negative cosine x. Okay, I know that that's a stretch. I'm out of time. I apologize. There is a problem on your homework that asks you for the 99th derivative of sine. So it's simple now because all you have to do is take 99 mod 4, right? And figure out which of these lists it lives in. Okay, see how the homework goes, 2.3, do all the homework, make sure you understand it before next class. We're way overdue for a quiz. And this is a type of quiz that I can do that's quick and it doesn't take a long time, right? Like you don't have to calculate a limit anymore. So I can just give you a couple of things, ask you for derivative, multiple choice. It'd be simple for me to do. So I think we should be ready for that next time. Yeah. All right. 2.3 homework. Have fun. See you on Thursday.
Thank you, Professor. Have a great day.
Try to keep you late.
Thank you.
Thank you. Bye.
I have a question.
Yes.
Oh, for the homework problem, you said for 99, you would take mod 4 for it.
Well, yeah, because it's asking for the 99th derivative of sine, it's the same as this problem, but 99. So the setup would be exactly the same.
Oh,
So
that makes sense.
yeah, so basically you'd still be using mod 4 because the jump between the numbers was 4. That's why we use mod 4. What would be interesting is, what is the 99th derivative, not of sine, but like of cosine? Because
Yes.
then this is going to be different, right?
Mhm.
But it still will change every 4 though. Like it'll go back to itself every 4. So you'll still have a similar setup, but it just won't be these 4 things matching with these numbers. That'd be an interesting exercise, but the one in the homework's 99. So you
Okay.
can just use this same table here.
So that whole mod, is that determined by what that function is? Like right now, we know for sine, it would be mod 4 because every 4 things change. And like you said, for cosine, it would be mod 4 because at every 4 things change. What if it's like cotangent? Would that also
Well,
be mod 4?
cotangent does not. Okay, so do you see how when we started here, we started with sine and eventually got back to sine and then back to
Yes.
sine? We call this cyclic. Now, that's not something that it's beyond the scope of this class, but it's called cyclic. It cycles, right? It keeps cycling. If you were to do like the 99th derivative of cotangent, it's not cyclic because cotangent doesn't go back to itself ever. It just gets crazy. The only ones that are cyclic are, well, the ones that we're going to study, sine and cosine. Those are cyclic. They will go back to themselves eventually.
Gotcha.
And they do it every 4 derivatives, which is why you'd use mod 4.
Understood. Thank you.
Yep, no problem.
You will be at office hours, right, sir?
Yes, I'll be there at 4.
See you then. Thank you.
All right, bye-bye.